After applying the changes in your OSPF configuration, what exactly is going to happen? In this video, I will take you on a deep dive into the OSPF neighbor adjacency process. Welcome to the network trip. Just after configuring the OSPF process in our routers, they will identify the interfaces where OSPF neighbors are expected. For example, if we have R1 and we have R2, R1 is expecting one neighbor out of that interface. So automatically, just after enabling the OSPF process, it's going to send that message there. That is a hello message. And that message will be sent to a special multicast address. And that address is 224.0.0.5. The main idea with that message is trying to discover neighbors out of that interface. That means routers that are willing to establish an OSPF neighbor adjacency and exchange routing information. If we configure OSPF in R2, R2 is going to do exactly the same. It's also going to start sending those hello messages out of all the interfaces that are enabled for OSPF. At that point, R1 and R2 are just trying to discover neighbors, but they are unaware about the presence of those devices out of that interface. A hello message is going to include information about the local OSPF configuration. If R1 is sending that hello message, it's going to include several properties for his own OSPF configuration. And basically, it's trying to announce that information to potential neighbors. And if those neighbors are agree with those values, they can say, okay, we can talk to each other and we can start exchanging routing information. But exactly what information is inside those hello messages and which of those values must match to successfully establish a neighbor adjacency. There are several properties inside that hello message, such as the hello and dead intervals. So let's talk a little bit about those two timers that will be included inside that hello message. So the first one, the hello interval. That means that that router is going to be sending the hello messages every 10 seconds. And then we have the second timer that is related to the hello interval, and that is the dead interval. And that is 4x the hello interval, in this case 40 seconds. If R1 is sending that hello message, it's going to include the hello interval and also is going to include the dead interval. So what exactly is the dead interval? The dead interval is basically that router announcing the neighbor, if you don't hear from me after 40 seconds, you can bring down our neighbor adjacency. And now the neighbor knows that if after 40 seconds he's not receiving those hello messages, then it's going to remove the neighbor and is going to execute the Dijkstra algorithm again, and is going to recalculate the best path to reach all the networks. Those two timers must match. The next property to match is the area ID. If that interface is mapped, for example, to the area 0, that interface must be in area 0 as well. If they are in different areas, that is not going to work. The next one is the subnet mask. It's important to mention that this restriction applies to all network types but point-to-point. If we are using point-to-point, this is going to be ignored. Let's assume that we have configured the IP 10.0.0.1/30 in R1's interface. But in the router 2, we configure the IP 10.0.0.2/24. The subnet mask is different, and that is not going to work as well. The next one is the stop area flag. That flag is basically true or false, or 1 and 0. And it's telling if that area is going to support external routes. If the value is 1, that means that that area is just a default area and is gonna allow external routes. If that value is 0, that means that external routes are not allowed in that specific area. Also, that bit must match to be able to successfully establish this neighbor adjacency. And finally, the authentication. There are 2 types of authentication in OSPF. We have ND5 and we have plain text. If we are using authentication, that type must match, and obviously the secret that we are using also must match. The best way for understanding the hello messages and the content and how this process is gonna go is by going to the action. So we'll go to the lab now. In this topology, I have 2 routers, R1 on the left, R2 on the right. They are using the network 10.0.0/30. The IP.1 is configured in R1 and the IP.2 is configured in R2. OSPF is configured in those 2 devices, but the instance is disabled. That means that now the OSPF process is not running. Those routers have been configured following all the steps that I explained in the video above. So we have the OSPF configuration and we only need to analyze how those messages will help to establish the neighbor adjacency. So let's check the configuration in R1. So I have R1 here. You can see that the OSPF process is disabled. I only have in that device the IP addresses configured, one that is connected to R2. Then we have an IP on Ether2 that is basically the local area network in that device. And then we have a loopback interface. The instance for the OSPF process is just setting the router ID. Then we have the backbone area that has been created. So you can see area 0, the area ID is all zeros. And then we have the interface templates. So here R1 is expecting a neighbor. R2 is not expecting a neighbor, so we'll say that this is gonna be a passive interface. And this is gonna be the interface that is trying to find neighbors. We are expecting just one neighbor out of that interface. We can use point-to-point as network type. And that's exactly what I have here. If I go to Ether1 on interface templates, we can see the interface, area, and network type. And then we have another entry for Ether2, the loopback interface, the area is area 0, and we have the passive option because we are not trying to find neighbors out of those interfaces. Now I'm going to R1 and I will start capturing all the packets coming in and out the interface Ether1. So let's go to R1, capture Ether1. This is going to open Wireshark. I'm gonna filter the OSPF packets only, so we can see that there are no OSPF messages. Going to R1 and I will enable the OSPF process. Just after enabling the OSPF process, the router is gonna start sending hello messages. So you can see just after clicking there, we got a hello message at the second 22. So after 10 seconds, we'll expect to see a new hello message, and that's exactly what is happening. And then after 10 seconds again, we'll have a new hello message. So basically this is R1 trying to discover neighbors out of the interface Ether1. At this point, R2 has also the OSPF process disabled, so they won't be able to talk to each other using OSPF. But let's see what's inside that hello message. What information that R1 is announcing to potential neighbors out of that link. So let's go to Wireshark and check the content inside one of those hello messages. So I will pick any of those hello messages, and if we go to the content, we can see that there is no TCP, there is no UDP, because this is just an OSPF message. We have the IP header, the source is 10.0.0.1, but the destination is a multicast address. And that is the all routers multicast address. So you can see that's a multicast address. And the source is the actual IP that is configured on Ether1. Then we have the OSPF header, open shortest path first. So we can check what's inside that header. If I expand the section, we have the header and also we have the hello packet. Let's go to the header. We'll see this is version 2. So we are using OSPF version 2 for IPv4. The message type, this is a hello packet. We have the packet length 44 bytes. The source OSPF router, this is 10.255.255.1. So we can see that that is the router ID. So if I go to R1 and I check the instance, we can see that the router ID is 10.255.255.1. So basically the source OSPF router. Then we have the area ID, all zeros. So we have here on the interface templates, ether1, we have the area 0 configure. And basically that information is also included in that hello message. Then we have the authentication type. This is null. If I check that interface, you can see that I'm not using authentication. So that's why this is telling I'm not expecting to use authentication. And then we have the OSPF Hello packet. If I go inside that one, we can see the network mask 3 times 255.252. And that mask is coming from the IP address that we configure on ether1. So we see /30, and that is 255.255.255.252. Then we have the hello interval, 10 seconds. This is coming from the OSPF interface template. If I go to ether1, down in this window, we can see the hello interval by default is 10 seconds and the dead interval is 40 seconds. And that's why we have that information here and here. And then we have information about the designated router and the backup designated router. In the upcoming video, network types in OSPF will go deeper with what exactly is gonna do a designated router and a backup designated router. So this is basically the content in that hello message. So we can see that there is no information about the neighbor. So it means that this is a hello packet and there is no neighbor and there is no active neighbor out of ether1. So now I'm going to jump to R2. Basically, after enabling the OSPF process in R2, what is going to happen is that R2 is also going to start sending hello messages. R1 is going to get that hello message. It's going to compare those values against its own values. If they match, they will continue through additional steps. So after enabling the OSPF process in R2, we'll get a bunch of messages. That basically is for exchanging the database, exchanging the routes, and finally they will have a synchronized link state database. I will go to R2, I will enable the OSPF process, and after capturing that bunch of messages, we'll go through every step. So now I'm in R2 and I'm simply going to enable the OSPF process. So we are expecting, we see here the hello message coming from R2. In just a few seconds, we are going to get that bunch of messages. A lot of black messages. We can see here a description message. We see a request message, updates, acknowledge message, and so on and so forth. So now the routers have synchronized their link state databases. And after having that information synchronized, we expect to see only hello packets again. We can see that they are just sending hello packets again. And now if we go to R1 and R2, we must be able to see all the routes coming via OSPF. This is R1. If I go to IP routes, we can see that we have 2 routes coming from R2. And if I go to R2, something similar is going to happen. We have 2 routes coming via OSPF. So what exactly are all those black messages? So I will stop the capturing process now, and let's see how those hello packets were exchanged. So here we have R1 trying to find neighbors. It's sending the hello message. This is exactly the same content that we checked before. But then after enabling the OSPF process in R2, R2 is also sending a message to the multicast address with information about the OSPF process in R2. So we can see hello packet, the router ID now is R2 because this is coming from R2, and we can see all those values. In the options, we can see that this is supporting external routing. This is the stop area flag. If this value is 1, this means that this is a default area, it's a normal area. It's going to exchange information about the external routes. Since this information is matching the values in R1, they are able to establish a neighbor adjacency. At this point, they are in the init state. So if we go back to the presentation, so now they are in the init state. There is no neighbor adjacency at that point. They have just received a hello message, but still there is no neighbor adjacency. R2 sent a hello message to R1, then R1 took the hello message, compared those values against his own OSPF configuration, and R1 said, yes, this is matching everything, we can continue. In the next hello message, R1 is going to include information about the active neighbor. And it's gonna say, I receive your hello message, R2. I'm willing to establish and exchange routing information. So if we go back to Wireshark, we'll see that the next message that was sent by R1 is going to include an additional field. They're going to be the active neighbor. We can see that value here. R1 is in a state that is called two-way. This means that R1 has received the hello message from R2. That's exactly what is happening. In the previous message, that active neighbor field was not present. So if we check the previous hello message, there is no active neighbor, but now that value is there and is sent to the all routers. So now R2 knows that R1 got its hello message. After that point, those two devices will decide who is going to be in charge of synchronizing the link state database. That is going to be the router with the highest router ID. So for example, if that were the scenario, that device is going to be the one in charge of synchronizing the link state database. That state is called X-start. After deciding who will manage that process, then they will jump to the exchange phase. So in the exchange phase, they will send a message that is called database descriptor. So basically, every router is gonna send a summary of the local link state database. This guy here is going to send a database descriptor message, and that device there is also going to send a database descriptor message. If we go to Wireshark, we'll see that exactly after receiving those hello messages, now they are sending the DB description messages. If we go to the first description message, this is coming from R2 to R1. We can see here that this message has the MTU value. If the MTU value in the interfaces is different, then these two devices won't go ahead and they will stop at this point. So the MTU value is in the database description message. Then we have some flags that are about the external routing capabilities. And then we have the database description. So here at this point, R2 is telling I'm the master, and also is telling that it's gonna send more messages for the database description. And here we have a sequence number. So let's check what is the next message that is coming from R2 as well. So we can see this message, and you can see that now the more bit is set to 0. Then R1 is also going to send a database description message and also going to include some information. This is the router ID in R1. We have the database description component. We have a sequence number as well. After getting the database description messages, every router is going to compare that summary against its internal link state database. If there is any information that is missing, then that information is going to be requested to the neighbor. And for doing that, those devices are going to send a message that is called the link state request. So R2 sent the database description, R1 compared that database description against his own database, then discovered that is missing some information, is going to request that information to R2, and then R2 is going to send an update telling, okay, this is the information that you need. R1 is going to acknowledge that and it's going to tell R2, I got your update. And that is called the link state acknowledgement. So we can see that all those messages have a very specific function inside this OSPF process. So first, the router got a description of the database in the neighbor. Then it's going to compare that one to its own database. Now knows what information is missing. It's going to request that information to the neighbor. The neighbor is going to send that information that will be loaded into the local database. And now this router is going to tell the neighbor, I got your information. And at that point, the databases will be synchronized. And then the second router is going to do exactly the same. After exchanging that information, those two devices will have exactly the same database. And that is a requirement for all the routers inside the same area. The database descriptor messages and the link state request are sent during the exchange state. Then the link state updates and acknowledgement are sent during the loading state. And finally, after having the database synchronized, they will go to the full state. And now they will start just sending hello messages. If there is a change on the state, if one link is going down or we are adding more networks, those devices are going to create a link state update, and that is going to be advertised to its neighbor. If any of those values is not matching, the neighbor adjacency won't be established. Let's see what happened if I change the MTU in one of the interfaces participating in that link. R1 is on the left, R2 is on the right. I will change the MTU in ether 1. Let's change it to 1450 bytes. I will disable and re-enable the OSPF process. And we can check the log at this point. And we can see that the neighbor adjacency is now in the X start. At this point, those devices are trying to establish the neighbor adjacency, but the MTU value is not matching. That this router will remain in that state, is not going to go to the full state. So let's check if router OS is going to provide some information. So it will enable the OSPF login topic here. And let's go to the logs to see if we are getting some feedback from router OS. So we can see that this is sending the hello message. Then there is a DD message that is received, that is the database descriptor message. But it's not going beyond that point. It's just getting the database description message since the MTU is not matching. If I go to ether 1 and I set the same MTU value, they automatically will establish the neighbor adjacency. So you can see this is going from loading to full, and now it's in the full state. The router has been installed, and now we go to OSPF. This is in the full state. So what happens if the interface has a different timer? So let's check that. If I go to ether 1 and I set the hello interval to 20 seconds and the dead interval to 80 seconds, and I click OK. So to accelerate this process, I'm going to disable the instance and I will enable that instance again. Let's go to neighbors, log, and we can see here an error message dropping hello from 10001. Hello interval missed match. So there is no way for establishing this neighbor adjacency. So let's go back to interfaces and set these values to the default values. So the next property is the stop area flag. So if I go to the area, so routing OSPF areas, and instead of having area 0, I have area 1, and I set this to stop. So basically here we are not matching two values, the area ID and also the stop area flag. If I apply those changes, automatically the neighbor adjacency will go down. And if I go to the log, let's see if we are getting some feedback from router OS. We can see the hello message is going. There is no information about the actual error. If I go to arg1 and we check the routing information, there is no information about that neighbor, but we can see that this is in the init state. So I will set back the original values. And finally, we're missing just the authentication. Let's assume that we are in arg1 and we are going to use authentication. Ether1, let's use MD5 and the authentication key, mikrotik, authentication ID, let's set this to 1. Okay, starting the OSPF process, we can see authentication mismatch. So now this error is explicitly telling what exactly we need to solve. Now you know how two OSPF routers are going to exchange information to synchronize their link state databases and how they will keep that adjacency alive. I hope this video is going to be helpful for you, and I see you in the next one. Thank you.